In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einstein
decimal place, so you can just put whatever you want there, and nobody can tell you nothing.
All right. Hello and welcome to episode 60 of Aether Roundtable. Tonight, Shane's going to be presenting on the optical equivalence for Earth curvature and the curvature of your vision. Whenever you are ready, Shane.
Excellent. Thanks, Alan. So we're going to be going over quickly the optic spreadsheet that breaks down, distance to the horizon geometrically on a globe versus angular resolution limit and limits of your vision, and how they mysteriously come up with the same figures and give you the same distance to the horizon, etc. So let's see here. First, let's take a look at the database page. The optics versus Earth curve database page is out there. This is the pretext that starts it off. It's essentially the main argument, right? It should have been taught in school, but it's not. If you were taught the limits behind optics and vision and angular resolution and how it applies to aperture in your eyes and optics, then they wouldn't have been able to teach you about the globe and how ships disappear over the horizon. So could be an argument made that it was specifically left out, not taught this way. But if you look into all these figures, and we're going to break down essentially the difference between an optically derived horizon limit and a physically geometrically derived horizon limit. They're going to be the same. They're going to be exactly the same. There's going to be a couple of equivalences and a couple of differences, but the equivalences at the end will be going over as well. The spreadsheet itself certainly be made available, but essentially just compares, an optics-driven diffraction limit horizon to a geometrically Pythagorean theorem derived horizon, right, based on a sphere of a given metrics and a given radius, 3959, can calculate the distance to the horizon based on an observer height, and the same thing can be done with your vision. And yep.
You are not rolling on YouTube, by the way.
Oh. Right. Yeah, that's fine. All right, there we go. Sorry. Good to go anyway. So we're going to start with the source. Pretty much the source of this observation and most of this math came from this one video, Life is Short, from Angular Resolution in Our World. So I'm going to link it in the description. Really, everyone should watch it. It's like 3.5 hours. It's one of those things where I say everyone should watch it, but I know nobody will. So we're going to do a quick little blurb, but it's super informative, and it's really the reason all of this math came about. I think it's also the pretext for the Euclidean versus non-Euclidean battle, where I think Gleam is referenced, and it's how the eyeball works and how a hyperbolic parabolic world is observed linearly or whatever. And of course, the main contention is that what if the Earth curve that you can get geometrically from a prescribed sphere of radius 3959 and angular resolution with the distance dependence distant dependent resolution, what if they're exactly the same thing, right? Of course, they always say it's because it's physical Earth curve, and now we're saying it's actually literally optical, and it's an optical loss of information starting at the horizon. And the math for that can be put forth by Life is Short here. So we're going to watch a quick little, I think 15 minutes of this. It starts with the summary. This is almost at the end of it, and he's going to quickly go through each of the points here, and I think the summary is really key because you can get all the information that he pretty much went over without going through the 3 hours. So we're going to watch the quick summary. It goes over the two positions, the math derivation thereof, and the quick comparison to see how they're exactly equal. So see here. Let's do.
Oh, I love this video. Nice.
Yep. Let's do 1.3. I think we can get away with.
So let's summarize where we've been up to this point. I want to impart to you that the loss of information at our horizon is an optical phenomenon. The ground is brought to eye level. Our eyes are not brought to ground level. Distant objects disappear by a combination of the angular resolution limit of the observer and upward refraction phenomenon. So option 1, again, the ground is brought to your eye level. The person disappears from perspective by walking straight away and vanishing bottom first from things getting smaller with distance and an angular resolution limit. And here's some of the examples that we've gone through to this point. We have our lid disappearing into the floor. We have some calculations that we can use to determine our horizon distance and or loss rate with height change. Let's now turn to our second option. So option 2 was we had the eye is brought to ground level. The vanishing person is represented orthographically without regard to perspective, and your focus continually shifts downward to observe them going over a curved surface and vanishing at the same rate. It just so happens to as the angular resolution limit of the human eye, and we will show that momentarily. So again, within this diagram, our eye line shifts downward. It must shift downward to observe an object physically going over curvature. Perspective effects and angular resolution are ignored.
So the orthographic
And
geometric
putting it
Earth
together
curve.
so you can see them side by side. The loss of information at our horizon, just to restate our argument, is either an optical phenomenon or a physical one. If it's physical, they disappear by walking over the horizon. And if it's optical, people disappear by angular resolution limit of the observer. So with these options in mind, we will now use the angular resolution limit of the human eye to calculate the radius of Earth. The first step in doing this is to assume a curve, and that the lower 50% of our vision represent a physical blockage of our vision. So we need to translate our linear perspective into an exponential one. So again, the angular resolution limit of the human eye is 1 arc minute, or 0.02 to 0.03 degrees. We have to get a more precise value though, or the range will be too high for the radius of Earth. So we need to plug in some good numbers for distance. Since we're seeing boats go over the horizon, we'll use a small pupil diameter because we're focusing at far distance. So again, the diameter of the pupil ranges from 2 to 4 millimeters in bright light and 4 to 8 millimeters in dark. Recall that refraction effects are highly varied, so we need a relatively non-refracted wavelength to get a more consistent value for a distant object. So orange-red wavelengths are less resolved than blue, but they are less subject to the highly variable refraction effects and atmospheric scatter that we witnessed before. Recall that refraction and diffraction are different. One is the change in angle through a new medium. One is the change in angle from passage through an aperture. So the wavelength of light ranges from 400 nanometers of the purple range to 700 nanometers of red. We want to use the more orange-red later wavelengths. Since we're looking at objects far away, we'll use an orange-red wavelength of 666 nanometers. The pupil narrows when it focuses on distant objects, like we said, so we'll use a pupil diameter of very low of 2.16 millimeters. So we can solve for theta using a predictable occult preoccupation with numerology and the number 9, such that theta in radians is equal to 1.22 wavelength divided by diameter, which is 666 nanometers divided by 2.16 millimeters. That gives us our number in radians, and which is also adding up to 9 as we'll go through. And that gives us a angular resolution theta of 0.0216 degrees. So again, I chose these numbers on purpose. The numerologies of 6s and 9s as 666, which adds up to 9, and 2.216, which also adds up to 9, and 3762, which also adds up to 9, are on purpose, very intentional. The subject is vast, but it is their mark, just like 24.3 degrees is 9, 66.6 degrees is 9, 432 hertz is 9, the sacred geometry of sound and cymatics. The seconds, minutes, and hours all are increments of 3, 6, and 9. There are Fibonacci pairings, flowers, and trees of life, and numerous other examples of numerology that seem to stem from Pythagorean and Ptolemaic schools, alchemy, Hermeticism, and Babylonian, Egyptian, Greek paganism. In essence, the 6 is man's number, the 9 is their God number, and the 666 is how man becomes God, as 666 is equal to 18, which is equal to 9. I won't go into that too much at this point. Just know that the numbers that I chose were purposeful. So we calculated theta as equal to 0.0216 degrees for long distance vision and a pupil diameter at the lower limit. So we can now use this angle to see how far the average 6-foot person can see, just like we did with our object examples before. So distance is equal to the height divided by tangent theta, which is now equal to 6 feet divided by tangent 0.0216, gives us 3 miles. With theta and our max horizon distance known at a 6-foot elevation, we can solve for the amount of information loss at that distance. So again, we flip the triangle back around, and this person at this height would lose 6 feet. So under optimal conditions with a minimum pupil diameter of 2.16 millimeters for long distance viewing and a wavelength of 666 nanometers, we can see that when looking 3 miles away at a 6-foot observer height, anything smaller than 6 feet below the horizon cannot be observed. We now have the 2 triangles with which we can construct a curve. We can fit the height and drop triangles together as we look down across the curve to view a distant object disappearing over it. So again, the first one is the distance that we calculated for a 6-foot person using theta at 0.0216 degrees. And the second one is the loss of information that that person would be granted across that 3-mile distance. And you can then use those triangles together to get your rate of curvature for a 6-foot person observing someone go over the curve. So as an aside, if we extend the lines, you can see that we underestimate the loss at this pupil diameter and wavelength nearby and overestimate the loss using curvature with greater distance. So again, if I assume a curve now that this green person essentially is walking over a curve, you see that the lines don't really match up between the triangle. The straight blue line and the brown line do not match up. The curvature rate is underestimating it nearby, and it is grossly overestimating it far away. So for example, at 100 miles, we expect to lose roughly 184 feet by angular resolution at 0.02 degrees. But with curvature at 100 miles, we're losing 6,660 feet. So the takeaway is that with distance, diffraction plays less of a role than refraction does. That's the takeaway here, because we do see the bottoms of things lost at a greater rate than simply 184 feet at 100 miles. By extension, the use of infrared camera technology is very useful over long distances since it is more prone to diffraction issues but experiences less refraction at the same time. So because refraction does play a decent sized role, that the infrared camera technology is proving to be a very good tool to view these distant objects, which again do not have anywhere near the expected rate of loss, such as 6,000 feet of loss at 100 miles. It just doesn't exist. So our rate of curvature is 6 feet lost at 3 miles from a 6-foot observer height. We need to approximate the angular resolution limit line within our curve as close as possible. We only have 2 crossover points, one at 0 miles and one at 3 miles. We know that the size change must be exponential within perspective in order to get a curve to develop out of it. Can't be linear. So we will solve for the Earth's radius by knowing the arc length and arc angle. You can see here we've just taken our 2 triangles, placed them against a curve for a person walking over at that rate of 6-foot loss over 3 miles, and we have then extrapolated it along a greater circle. So the observer would assume they are watching a person descend from their point of view across 2 theta at 3 miles. The first theta, 0.0216 degrees, would represent the observer height at 6 feet until reaching 0 feet, and the second theta for the drop from 0 feet to minus 6 feet. So we can therefore take our arc angle of 2 theta across an arc length of 3 miles, or we can take the drop rate of 12 feet across 3 miles. Either will give us r for the greater circle. We can now solve for the radius of Earth from the angular resolution limit of the eye as our segment here with r along the radius or along the one aspect of the triangle and 3 miles as our opposite end, and the angle being across 2 theta, which is 0.0432 degrees. That will give us one number, and the alternative is to use the ratio of 12 foot over 3 miles is equal to 3 miles over r. Both will give us the numbers listed below. So we get for one number 3,978 miles, and for the other one 3,959 miles, giving us an average of 3,969 miles. So for our circle based on the angular resolution limit of the human eye, we can calculate a radius of 3,969 miles, and the circumference then comes out to 24,938 miles. And coincidentally or not, the Earth's radius is said to be 3,963 miles with a circumference of 24,900 miles. We can then calculate the drop rate and horizon gain that comports to a curve with a radius of 3,963 miles by pulling out our triangles as below. So if I now deconstruct these triangles that we used to get the curvature rate, we can get either a horizon gain or a height loss or drop rate. So recall that within option 1 of the angular resolution, horizon gain is nothing more than the expansion of the lower eye-line resolution angles, or theta expansion. And the height loss or drop is nothing more than the compression of the lower eye-line resolution angles, or the theta compression. So we can then extrapolate these two triangles to a greater circle again and calculate out for a circle what we would have as a height loss or drop, which is again just the theta compression, or the horizon gain using trigonometry, which is again the theta expansion. So for the circle here, with this particular rate to create a circle, you need sine theta is equal to, where theta is that arc angle there between the distance over which you're observing something drop. It's equal to the distance over which you're observing it drop divided by r, the radius of Earth, which yields that angle. And then you're going to solve for the height of that drop, such that the height is going to equal the radius minus the radius times the cosine theta. And you can see from the trigonometry there how you get those angles from those arc lengths and so forth. You can alternatively get a horizon gain or theta expansion formula pretty simply by just using a right triangle. So in this right triangle example, you're going to have r plus a height of u sitting above the surface of the circle. Squared is going to equal r squared plus d squared. You can see just the edges of the right triangle there. And you can then solve for the distance d. The drop h squared is, since it's small, you can just subtract it from r squared from both sides, and then d becomes the square root of 2hr, or distance in miles is equal to 1.22 times the square root of height in feet. So if you just plug in your height in feet above the surface of the circle, you will get the distance d across which you can see.
Whoa, I didn't mean to do that. But that 1.22, that's a crazy constant that always comes back around. That is present in Rayleigh's criterion specifically, and in the distance to the horizon geometrically from a Earth ball. So it's funny that that constant comes out on both sides, but it also, of course, leads to the same result. But
expansion formula, pretty simply by just using a right triangle. So in this right triangle example, you're going to have r 1.22 times the square root of height in feet. So if you just plug in your height in feet above the surface of the circle, you will get the distance d across which you can see. And you can see the exact same formula here on the Wikipedia horizon example, saying that the average person, say about 6 foot, can see about 3 miles, which is again just angular resolution. So we can also derive a quick calculation formula any number of ways. We need to determine the exponential rate of loss across a change in distance. So in other words, we need to know what the loss per mile is with each additional mile, or the x loss of feet per mile squared. We can then model this rate of loss two ways. One ignores perspective and models a standard height that experiences an exponential drop rate, or attempts to incorporate perspective and models a standard drop rate across an exponential size change. So here we have our two possible ways to model this, but the same equation. You have a standard drop rate x across an exponential height change, which you could then place into perspective to view something getting smaller with distance and parts of it getting cut off with that distance. So height is equal to x, some constant that we are, it's going to be some unknown standard rate of loss across 1 over the distance squared to give us our exponential height change. And in the other way, we're going to use the same formula, but we're going to be using x here as our unknown exponential rate of loss across a standard height. So again, on the first example, we have an unknown standard rate of loss across an exponential height. And on the second one, we have an unknown exponential rate of loss across a standard height. Both give us the same information. If you need to pause and digest some of these, please do so. Either way, we need to find the drop rate x. So we'll use the standard drop across an exponential size change in order to view this person in perspective. So if we believe the rate of loss is 6 feet for every 3 miles, starting at 0 feet and 0 miles, which are again our two matching points between linear angular resolution loss and our exponential curvature loss, we can then solve for x. So remember, we need to know what the loss per mile is with each additional mile, or x loss of feet per mile squared. So the 6 foot loss at 3 miles becomes a 6 foot loss at 3 squared miles, or a 6 foot per 9 mile squared loss, or 0.666 feet per mile squared. So again, you can change our formula, essentially, or the way of looking at this diagram, to be a just substitute x for what we solve for as 0.666 feet per mile squared, and this person has that part of him essentially removed with that particular distance. So you can see at 1 mile, he has chopped off about 8 inches of his legs. At 2 miles, he's lost about 2.6 feet of himself, or about half of his body. At 3 miles, he's lost 1 full body. His 6 foot has disappeared. At 4 miles, he's lost to about 10.6 feet of himself. In other words, if we remove 0.666 feet from the object across the square of the distance, this is what we're doing in order to theta adjust our height in perspective. You can then just take 0.666 feet per mile squared and you convert it to in inches. It becomes 8 inches per mile squared, which is the common formula that people use. Again, this is not terribly accurate. It's only accurate up to about 100 miles, as we'll see, because it works out to a parabola. It's not a circle. We can place this person into a perspective view in an attempt to match our reality, like we talked about, but this often fails to match what we observe because the math was used to fit a false assumption. In other words, keep in mind these formulas are not accurate, but I wanted to show the derivation. Again, the truth of the world is that it is linear. So again, the loss per mile, 0.666 lost below the knees, then we have 2.6 lost below the waist, then about 6 foot loss, which is the whole body, and then about 10.6 loss, which is almost 2 bodies. And our inverse square law adjustment here, you're going to be at 1:1 at 1 mile, 1 and 4 at 2 miles, 1/3 squared at 3 miles, and 1/4 squared, 1/16 at 4 miles, and so forth. So you can see the conversion there going from right to left, and then you can just place that person within the horizon line and you see what you are going to get chopped off at various distances. So one person here is going to get his legs chopped off at 1 mile. He's going to get half of his body chopped off at 2 miles. We're going to lose an entire person at 3 miles, and we're going to lose 2 entire people, or almost 2 entire people at 4 miles. It's just going to keep going from there. So I just took the picture on the right, and you just chop off a portion of it and you move it into perspective. That's all that's being done. It's an exponential size change with a standard set loss set against our perspective view. And this is somewhat of our theta adjusted parabola, or a parabolic loss. So it can be used to estimate a curve again, but it's only good to a certain point. It works up to about 100 miles, as you can see, and then it just starts to fall away. You cannot make that come back into a circle. So it has a slight overrepresentation of loss, but then greatly underestimates the circle as it goes on. So again, the two curvature formulas are roughly similar to 100 miles, and then they start to break down. Whereas our linear loss, you can see that what we actually lose within our linear world is way up there. So it's much more of a dramatic loss that you have to have in order to live on a curved surface. You have to have these high rates of curvature and loss of an object. So what that means is if you do see an object and you see more of it than you should, it should bring into question that this is a physical phenomenon, that you are losing this object physically behind curve. We already have the quick formula for height gain according to the circle model, and the assumption that we look down across a bulge of Earth to see distant objects, but the distance across a height gain is simply the inverse scenario of the height drop across a distance, so we can invert the drop rate of 0.666 feet per mile squared as the height gain and horizon distance gain. So the parabolic height loss or drop is then just inverted to become the parabolic horizon gain. So our height equal to 0.66 of a drop rate across the mile squared is then inverted. The h becomes 1 over h. So then 1 over h is equal to that same rate. And we can then solve for distance, and it becomes 1.22 times the square root of h, like we derived earlier. And they are, again, very similar in that respect. So the parabolic horizon gain is much more accurate to a circle. But again, the drop formula, when plotted out and compared with the circle, works very well up until 100 miles. And after that, that aspect of the formula breaks down.
Nice. Right. So that's a whole bunch of stuff. That's only like, I think, 20 minutes of it. But he goes down, he breaks down the entire basis for Earth curve, the basis for geometric distance to the horizon. If anyone's ever been to 24/7 Flat Earth server, I think you might have heard, 1.22 times the square root of the observer's height in feet, because it's used to portray the black swan, right? That's how they get the maximum horizon distance. And they say, look, this observation falsifies the globe, therefore, because they saw the horizon distance calculated at the observer height based on where the camera was, right? And did the calculation batch for the maximum horizon distance, and that's how they say it falsifies the globe. So all this math keeps coming back to us, right? And I just thought it was super interesting that you can derive the same values, from the limit of optics and Rayleigh's criterion using the same constant of 1.22. And then you can do the same thing geometrically for a sphere of that radius, right? So I thought those two derivations were super interesting. I think this one in particular was super interesting because you can do it. He does pretty much the basic distance to the horizon formula, right? They do like a right triangle and then Pythagorean theorem just to get this distance. And they're like, just because this is the height, you take this from where you are of the observer, you draw a line straight to the horizon's edge, you draw another line through the center of the Earth, and then you solve for this over here. And this is this math that he was using. So I think that excellent way to derive it, right? Geometrically, for a sphere this radius, this is how you get distance to the horizon when you're standing on this sphere. And then you compare it to using the small angle formula and the basic trig function on how to get distance based on angular resolution and optics. Comes out to exactly the same thing. I thought this part was super interesting as well when he actually, I think this looks like something Stone would make maybe. This is super accurate up to 100 miles. Everyone always talks about the comparison. You know how they say 8 inches per mile squared? That is the, parabolic function, meaning that it's this one. And they say that it doesn't matter which one you use because it's the same at 100 miles, meaning as far as you can possibly see, it doesn't matter which one. But way out here, it definitely matters. Everything that we see so far follows this linear line, and nothing has ever been verified to do these ridiculous drop-offs for parabolic or for spherical. It only ever does this. But because no one can see past 100 miles, no one's ever been able to tell, right? So again, bring us back to what we started with. This is just the basic. This is the basis for this spreadsheet, which is just comparing, optically and geometrically. Hey, look, the same distance to the horizon based on your observer height will always come out. And it, you can backwards derive the radius of Earth that way from the limits of optics in the human eye, as we started with. But again, he went over the occult derivation of that. He likes to use those numbers and talked a lot of 6s and 9s. But if you paid attention to what the optics were based on, it was absolute middle of the world optical conditions for a regular observer, for regular conditions, for the most refraction, to try to be the most generous we can to the other side to pick these variables. And then of course comes out to exactly the same thing. And if you ask AI why they're the same, they're like, oh, it appears that it's exactly the same as Earth's curvature rate. I guess it implied that our eyes evolved to resolve objects to the precise distance where Earth's curvature would hide them from view. I thought that was hilarious, so I wanted to share that with everyone. What an AI would think, wow, that must have been God's trick or whatever. Well, it's someone's trick, right? So again, the two approaches yield the exact same results. So the diffraction limit and the wavelength of light and the average diameter, and again, gives you the 2.97 miles to the horizon. And again, the same thing geometrically on a ball of radius 3959 comes out to the algebraic derivation, including 1.22 times the square root of the observer's height in feet. That's what this comes out to. And it equals the exact same thing. So then my question is, why the 1.22? I'm not sure what the correlation is. If anyone happens to know, definitely let me know. I'm super curious. On both sides of the formula, you end up with this super important constant that you need to make any of the math work. And again, this is distance to the horizon formula coming up from the globe. It's just basically one for one. It's the same diagram we started with, right? The same math. This is just, if you were to handwrite it, cross it out, do some long division, get it out, and then you can finally cancel it out, and you find it equals the 1.225 times the square root of the observer height in feet. So it's the same thing. So Rayleigh's criterion, 1.22, you need it over the wavelength and diameter. That's the constant to get theta. And in geometric Earth curve, you end up with it as exactly the distance to get the distance to the horizon. So why? Why is it? Look into it, you'll come to this. Bessel function as a first series of zero, and it's some sort of essentially like flower of life pattern when you do the what's it called? The Fibonacci spiral. It's essentially something like that. Honestly, I can't make sense of that. I don't know why. It's definitely referenced in the Airy pattern, which is the two discs that you use with Rayleigh's criterion, where they try to resolve where one's resolvable. It's present there, but why it ends up in both sides of the equation there, I have no idea. I would like to know. I would like to know. The main point, though, is that you can always derive it exactly the same, and that there's a kinematic equivalence between optically deriving where you can see the horizon on a flat plane and mathematically deriving it where you would see it on a geometric physical ball of 3959. It's exactly the same. So, like, if you were in school, right, and you had two kids who gave you the exact same answer, but they both use the same work to show you 1.22 times, what would you say? Would you say that one cheated off the other, or that they were both separately brilliant? And that's pretty much it for tonight, guys.
Dude, that's incredible. They're just the same, huh?
Right? Like, would you put those two kids in detention, or would you be like, listen, Johnny and Sam, you guys are both equally separately awesome?
You know what's crazy?
I'd be like, you two are fucked. You guys cheated off each other, didn't you?
I think the main real takeaway is the fact that like option 2 that he presents is that they ignore all of the angular resolution limits of the eye and the optical phenomena that happens in the eye.
That's
Right.
true. That's true.
They just literally ignore it.
So obvious, dude. If you start account for any of that, you immediately lose the Earth radius and all
The
that.
ball.
Yeah, the ball's gone. As soon as you account for the curvature, you can see that your eye is a ball, right? Like it's spherical. But when you get to the limit of your vision and you can't see anything, they're like, oh yeah, so instead of like things being farther out, people are just under you. Like, oh, okay, dude. Nice. Hell yeah.
I like how he quantifies all of option 1. Like, here's the angular resolution limit. Here's how you can do the small angle formula. Here's how it used. Like, you can use it in stellar parallax. You use it in gauge distance. It's absolutely mathematically viable. It describes the real world. Now, here's what happens if you ignore all that. And it's like, oh shit, that's the Earth curve. Oh, right. Okay, I got it. I see what you did there. It's like all the stuff that we know exists that is quantifiable, we summarily ignore and dismiss, and then scoop up with a giant pan anything we can and put that in the Earth curve bucket so that there's something there. That's really how it's done. It's terrible.
So anyone presenting, some type of distortion or bottom-up obstruction is based on Earth curve, we should just ask them, like, did you account for any of the optical effects that affect your eye in the observer? They're gonna say no.
Right? Or if you're gonna claim refraction or whatever, you're gonna take the temperature, you're gonna do the gradient, you're gonna tell me what the time of year it was, where the sun was, you're gonna tell me the time of day. We're gonna have to know exactly where. Like, there's no way. There's no way that they can actually predict those things ahead of time. They can only retroactively, mathematically make them go away.
Exactly.
But
That
this one,
1.22 that you were, so that relating back, like that is in the natural cycle of plants. Like a plant will do a 100 or one, like will do the 1.22 radius around before it grows another like leaf
Petal.
or another
Yeah.
sprout or another petal. So that is that natural flow cycle from the Fibonacci. So
yeah,
that's
that's
for
the only
nature.
that's the only thing
Shane.
I found is they were loosely related to that.
Quick question for you. Do you have a coefficient to account for carrots and how they can extend your eyesight and give you night vision?
Actually, yeah, we used 5 for that. It actually came out to 0 though, because that's retarded, so it canceled right out.
Okay. Just checking.
I like how
Also,
that's an objection.
also, Shane, you still have the title "Occupied Viewing Party" on Twitter.
Yeah, that happens like
Might be helping
every
your views,
second
though.
time now.
Yeah, that does happen every now and
It
then.
happens a lot for Twitter,
He'll
dude.
go live on like reading night and it's like Flat Earth Friday episode 117 or something.
He says like he's never done it, but I've caught Alan doing all the same.
I've never done it. I have no idea what you're talking about. Perfect.
Actually, I've seen most people screw that up on Twitter. Dude, restream is abound. It's
Yeah.
too late now, though. Thanks, Beast.
Yeah, no, but great prez, man. Great. And thank you for condensing that guy's 3-hour prez that I would have never watched into a 15-minute video that's digestible of
Seriously.
the main points.
Yeah, that's pretty much
And-
the entire point. Like, he breaks out all the examples beforehand, and it takes a long time to get there. But those are all the images that I end up scooping. Like, before I even saw that, I saw these images, and I was like, this is it.
Like, there it is, the curvature of
Oh,
your
man.
eye. So you're
Like,
telling
no
me
way.
you're telling me the spherical excess of your eye will match the spherical excess of the globe?
Like, I saw this by itself with no context, and then I just started reading it, and it was like, how do I fit this into things I already know and believe? But then I finally watched it, and I was like, oh, I see what he's doing. And then it neatly fit into what I was trying to make it do anyway.
Yeah,
I
what
just
was
had the
his name
proper
again?
Context.
What was his name
So
again?
Life is Short. Yeah, it's I put the link in the chat.
Shout out to Life is Short. I'll
Yeah,
put
it's
the
called
link
Angular
out as
Resolution
well.
in Our World. The dude has like 7 videos, and this one has like, I don't know, 30,000 views or something. It's like 80% of his channel. Then the rest of his videos are just, I think, dissected pieces of this one. This is like his claim to fame. I think it's been out for a long time. It's probably one of the most influential YouTube videos that you've never seen.
Nice.
Looking at diagrams like this one, I keep expecting to hear the commercial soundbite. Ho, ho, ho.
Green
Okay, you
giant.
guys. Exactly. There's somebody who knows who the Green
I didn't.
Giant
Yeah,
is.
I had
Right
no
on.
idea what he was talking about.
Yeah, you
Oh,
lost
oh,
me.
oh.
Never seen it.
Green giant vegetable commercial. Yeah.
Yeah, corn and beans, guys. That's all it is. That's all it is. Corn and beans.
All right. So does anyone have
Thank you
any
so
questions?
much, Shane. Yeah.
Speaking of green
Yep, nope,
giants,
Yeah,
Kinda-
thank you, Shane, so much for filling our cup of knowledge. But can anybody
Thank
tell
you,
me
Shane.
what I could fill my coffee cup that's empty in front of me with?
What a segue, Queen! Wow.
Thank you, first of all, Shinji. That was incredible. Oh, speaking of coffee, I gotta warn you guys, and I gotta warn you guys and alert you guys about something important. You remember I told you about those little grays, the ETs that came and stopped by my yard when I was drinking coffee? Well, okay, so they kind of like bullied me and took a bunch of my coffee, and then I had to order more. And then I found out a few days later, these other ET aliens from another distant galaxy stopped by. They came onto the yard, and I was like, "Holy cow! There's some other ETs here." And they were like, "Oh yeah, we found out about your." Oh, they were talking telepathically, by the way, and so they told me sent me thoughts, and they told me that they had a paid spy, like a paid agent from the little grays, and these were the tall grays. They didn't have the big eyes; they had normal eyes. But anyways, so they had a paid guy, like a trader from the little grays, who told them about the coffee and how much bliss it was bringing his people. And so they demanded to have some of the coffee. I was like, oh, I got scared, so I gave them some coffee. And now I had to order a whole bunch more. So you guys had better hurry up and order a bunch of brush tail coffee, because the ETs have found out about it and they're all coming and getting it all, they're buying it all up. So I told them that if they want more, they're gonna have to give me some gold, and they were like, "Oh, no problem, we got loads of gold." So, anyways, hopefully I'll make some profit off of it. But folks, just get on the brushtail coffee wagon and get your share now, because the ETs are after it. They all have spies. They're all telling each other about it, and we might not have any left. So hurry up and buy Brushtail Coffee, the best coffee. It's fair trade, shade grown, and even if it's not certified organic, the farmers practice sustainable farming and organic farming. It's really great coffee. So buy it now while you still have access, okay?
We may or may not
Damn.
be using a false scarcity tactic to sell our coffee, but that doesn't mean you shouldn't buy it, right? Now, if you guys want to see an interesting movie, like a reenactment of what Lily was just talking about, there's a movie from the 90s called Independence Day with Will Smith, where aliens from some other galaxy invade Earth and they want coffee. So check that movie out. Thanks for that ad, Lily. Much appreciated. Your check is in the mail.
Coffee's in the mail.
Alan G, you're implying I'm lying. I'm not. These aliens are real.
I think you were just implying that you were paid to talk about aliens.
All right, lads and ladettes, thanks for tuning in. Much appreciated. Tune in with us on Thursday for Research and Reading Night. And I think Witsit will be doing a Schooling the Globers night on Wednesday, maybe. So check that out. And then Friday, of course, will be Flat Earth Fridays, episode 121.
Nice. Yeah, thanks everyone.
Good prezzo, bro.